Oh, how did I end up here? Be reading outside, but I feel like that it's snow day. Leadership is speaking of no single body pages. All this snow day? I don't know when. I don't know. Here's what you think about. I know you watch out. Like power. Why will it not scroll? Yeah, page 19. Thursday, and we can be doesn't your community come or I go free to make it or you know, because my you know, around 8 and 2:40. I'm just doing more time to play with it. Right. You put in your make one fresh off and it's time to do some origami for notes are happening. These are taking too long. Vancouver Golden Knights ticket. Apple Airport 4. A Soldier Korea. A Solo Cup 26. Toronto League Locker Ball. A Goose Water Tour Drone. Phoenix and Wake more. Get ECR put on the game posters. The full list of 5. So if you, last day we said, if you want to find if an unbalanced half reaction is oxidation or reduction, you find the oxidation numbers. If the oxidation number goes up, it's oxidation. If it goes down, it is reduction. If you balance, or you can balance the half reaction and see whether the electrons are in the reactants, in which case it is reduction, or if they're in the products, it is oxidation. Now we're going to add on to that, and this is something that I told the other class yesterday, but I didn't get around to telling you guys. If you add oxygens onto an element, now what do I mean by that? What I mean is that, take a look at this one. We started with Mn, and then we have MnO4. We put oxygens on there without seeing anything, without finding an oxidation number, without balancing anything. I know that's oxidation. Okay? And the reason is that I'm putting oxygens on there. They have -2 charges. And so that means that the manganese is going to become more positively charged to balance out those negative charges. Okay? Also, and I found this one was really helpful in biology. If you add hydrogens onto an element, that's reduction. Which one do you think? If you have a negative hydrogen, what's the only time you're ever going to have a negative hydrogen? When it's with a metal. So are we going to be doing anything with metals in biology? No. No. Okay. So if you add hydrogens onto an element, it is almost always reduction. And if you remove hydrogens off an element, why did I spell element with 2 L's? That's weird. Okay. Element, that is oxidation. Now, these 4 are not like foolproof, okay? Because it also depends on what's happening to the charge of the species, the overall species. That's going to affect it as well. But this is kind of like something you can use just as a quick reference point if it happens to exist. But it's not foolproof. Yes, it's not 100%. what did I say in the other class? I had a good word for that when I said not 100%. I said it was not a surefire method. I like that way of saying it. This is not a surefire, right, correct 100% of the time kind of method. Where, how, there we go. This is not, these ones are not a surefire 100% guaranteed method. The other two are, if you find the oxidation numbers and that oxidation number goes up, it has been oxidized. Yes? If the electrons are in the reactants, it has been reduced. But this one is just kind of like, I'll do it this way, and then if I have time later, I will check it to make sure. Does that make sense? Okay. Do you remember the order of the 4 things that we balance when we're balancing half reactions? What's the first one? Major. And what do we mean by major elements? Anything that is not oxygen or hydrogen. And what comes after major? Diminished. Augmented. No one wants an augmented chord. Flat 7, raised 7, I don't know. Major had OH says charge. Okay, so major, do you remember what we use to balance the major atoms? Coefficients. What do we use to balance oxygen? Water. What do we use to balance hydrogen? H plus. And what do we use to balance charge? Electrons. Okay, so let us, do you guys want to try this one on your own? Yeah? Go for it. And you know what I would do? I would write it with these kind of in the middle so that you can add on to the left and you can add on to the right.
Oh, yeah. Huh? Wait, no.
Are we good with 6 water? Did we get a coefficient of 2 and 6 waters? Excellent. And remember, when you get to the charge, I would highly recommend keeping track of it on either side. What is the charge on the left? 0. And on the right, we have 2 negative and we have 12 positive. So overall, that gives us 10 plus. So to which side do we add electrons? The side that is more positive or the side that is more negative? We add it to the more positive side because we're adding electrons. We're going to be bringing that charge down. So add electrons to the more positive side. How many electrons do we need? 10. You need to show this. Well, what else would you need to show? Like I said, I recommend doing this because I know I've messed up on, like, you know, just because my brain is a messy brain. If you have a tidy brain where, you know, you don't make stupid mistakes, you can probably get away without doing that. But I have a messy brain that, like, loses things. So I like to keep them on paper so I don't lose them. Is good? Okay, excellent. Is this an oxidation or a reduction half reaction? Now, before we do that, let's just look at our unbalanced reaction for a moment. Here's our come on, move. There we go. There's our unbalanced reaction. Could you tell me what you would instinctively say this is using our little rule that we learned this morning? This is oxidation, right? We threw some oxygens on it. We oxidized it. So let's check and see if that is true. Is it true that this is an oxidation? Yes, because number one, what happened to the electrons? We lost electrons. And what is the oxidation number of I2? The oxidation number is 0. And what is the oxidation number of I in IO3 minus? It is positive 5. And if you're like, how? I'll quickly do that. We have I plus 3O equals negative 1. I plus 3 times negative 2 equals negative 1. So I minus 6 equals negative 1. So I is plus 5. And I wrote 0 because my brain is messy. Plus 5. There we go. So the oxidation number increased. Therefore, that is oxidation. Excellent. So we have proved it 3 ways. Stuck oxygens on it, lost electrons, oxidation number went up. I don't know why I left so much space for that, but that's okay. Now what we're going to do is we're going to take this one, and we had it balanced in acid, yes? In acidic solution. Now we're going to take this same reaction that has already been balanced in acidic solution, and we're going to change it to base. And really, all you're going to do to make it basic is you are going to add enough hydroxides to neutralize all of the H pluses. So, how many H pluses do we have? We have 12. So what we're going to do is we are going to add 12 OHs. But we have a little problem. And our little problem is that this reaction was balanced. Yes, we balanced it in acidic solution. It had the same number of atoms of hydrogen and oxygen. It had the same charge on each side. And now what are we doing it to by adding those 12 hydroxides to the right-hand side? We have, well, messed up the balance. So what would we have to do to keep the balance? Add it to both sides. So 12 hydroxide to the other side as well. And then we just add it up. So now we have 6 water plus I2 plus 12 OH minus goes to 2 IO3 minus. Now, instead of writing 12H plus 12 OH minus, what does that become? 12 water plus 10 electrons. And finally, what we do is oops, that was H2O, not just 6H2. We look and we say, is there anything we can cancel here? Is there anything that is on both sides that we can cancel? We can cancel 6 of the water. So what we're going to do is we're going to take all 6 of those and get rid of them. We're going to take this and turn it into a 6. If you want to rewrite the whole thing, you can, but you do not have to. Okay. All right. So that is what was described in add enough hydroxide to neutralize the hydrogen. Make sure you add them to both sides. Turn the hydrogen and hydroxide into water and then cancel anything that needs canceling, which when you just read out the rules and you haven't seen it in action seems to make very little sense. Hopefully, does seeing it in action make it make sense? Yes. Okay, excellent. All right, so let us try another one here. First of all, can you guess whether this is oxidation or reduction? Reduction. Okay, we got rid of some oxygens. There are fewer oxygens than before. And the charge is not significantly different, so you can be like, ah, yeah, that's reduction. So you guys want to try this one on your own? Yes? Okay. When we're reducing? When we're undergoing reduction, the charge becomes less positive because it's gaining electrons. Okay. It's reduction because we got rid of some oxygens. Okay. Now you're going to prove that to yourself by balancing it. Go off and balance. Yeah. How much OH do you add? 4, because you need to neutralize all the hydrogen. So if you have 4 hydrogens, you need 4 hydroxides to neutralize the 4 H's. Oh, huh? Yes, start from an acidic solution. Okay, so you do steps 1 through 4 in acidic, and then you turn it to basic. So start by balancing in acidic with your waters and your hydrogens, and only after it's balanced in acidic will you turn it into basic.
Like you add electrons first.
Yep. Because you want it balanced. You want to have a balanced reaction. You want to be like, it is balanced. And then you're just like, I add the same OHs to each side and it stays balanced.
Oh.
Right?
All of them. We're just two.
So does it make sense that we have done this balancing in acid? And then, because we have 4 hydrogens, we add 4 hydroxides to neutralize. But in order to keep it balanced, we add 4 to the other side as well. Is good? Do I need to do anything at this point? I need to cancel my waters. So 2 of them go away, and we're left with 2 there. So mainly with this, it's just a matter of practicing it so you become comfortable with it. Okay, once you've got the rules, you just practice. And look, so much practice for you. So what you might want to do is you might want to be like, oh, okay, well, I'm going to do some of them over in column number 1. Those all seem to be acidic though. So if I feel like I'm getting pretty good with those, maybe I'd pick one that looks kind of complicated. You know what I mean? It will say whether it wants it to be acidic or basic, unless, do you see these ones here? There's no oxygen. There's no hydrogen. All you're going to need is electrons. So is it going to be acidic, basic, or neutral? Neutral, okay? And then over on the right-hand side, there's a whole bunch that are in basic, so you can try those as well. So do a mixture of those, but we're not going to do it now. And that's okay, because you will still get practice when we balance full reactions, okay? Because part of balancing full reactions is balancing half reactions. Step number 1 of balancing full reactions is to balance the half reactions, okay? And we're going to start with a very, very simple reaction, 2 very simple half reactions. And this is on page 22. Page 22. First of all, we have our reduction. And we have our oxidation. And these are our half reactions, yes? So I have a balanced half reaction and I have a balanced half reaction, yes? Now, if I were to add those two up right this second, what would happen? Would I have the right number of electrons being transferred? No. So I cannot just add two half reactions and get a whole reaction. What I need to do is I need to not have 3 electrons coming out and 2 electrons going in. I have to have the same number of electrons being lost and being gained. Yes? We want 6 electrons. So basically you're making sure that the number of electrons going in is equal to the number of electrons coming out. And we just multiply the entire half reaction. So the trick of it is that you balance the half reactions and then you multiply the half reactions so that the electrons in equal the electrons out, and then you just add them back together. Okay? So you find the LCM. The LCM of 3 and 2 is 6. So we say, let us multiply our aluminum half reaction. We're going to multiply that one by 2. So everything in there gets multiplied by 2. We have 2Al, we have 2Al3+, and we end up with 6 electrons. Our copper reaction, we are going to multiply by 3 because that's going to give us 6 electrons. So we have 3 coppers, 6 electrons, and 3 coppers. Once we have the electrons in, matching the electrons out, those two are equal, then we can add them back together. And so we just put one right over top of the other. We make our arrows line up so that everything on the left side of the arrow ends up on the left side of the arrow, and it's easy to see. So we line up the arrows. You don't have to, but it makes it easier. And sometimes it's nice to have your arrow kind of in the middle of the page so that you've got an equal amount of space on either side of that arrow. And then we take our 2Al, we take our 3Cu2+, and the 6 electrons going in cancel with the 6 electrons going out. And then we got our 2Al3+ and our 3Cu2+, or sorry, Cu. How many electrons appear in this overall redox reaction? 0. You should not see electrons in a redox reaction. If you are balancing a full reaction, there should be no electrons. You will see electrons in half reactions, but not in full reactions. So you should never have electrons in a full reaction, only in half reactions. Even though I tell you this, there's going to be somebody, I don't know whether it's this block or my other block, who gives me a full reaction, and there's going to be electrons in there, and I'll be like, oh. And you're like, no, that's not possible. And yet, some people gave me a Ka for when we had a base. So, you know, it happens. You'll make that mistake once, and then hopefully you'll never make it again. What? On a quiz. Yeah. On a quiz, right? Because you've only sort of like started learning it, and things are a little bobbly in your head still and whatever, right? That's why we have quizzes, though, to get those nasty things out of your system so you don't do them on the test, right? All right. Note that in the overall balanced equation, the number of atoms of each type are the same. So basically, we've balanced the atoms. The overall electrical charge is the same. It is equal. So you have to balance both atoms and charge because there's a conservation of matter and there's a conservation of charge. And both of these rules also apply in half reaction, but in an overall reaction, we have, as we said before, no electrons in the equation. Only in half reactions. Okay? So here is how we balance overall redox reaction. You're going to be given a full reaction. It's going to be unbalanced. Don't try and balance it using grade 10 methods. It will not work. At least 90% of the time it will not work. Or it'll mean you're bashing your brains against the wall. Isolate the two half reactions. Balance each half reaction separately. Make the electrons in equal the electrons out, and then add back together and cancel where needed. This will balance it in acid. Let's put in acid here. Because it is the most efficient thing to do. If it says in base, to wait until the very end, wait until you've got your full balanced reaction and then make it basic, just like we did a moment ago for a half reaction. Okay? You can do it with the individual half reactions, but that means that you have to do it for each one. So you're doing it twice rather than just doing it once. And if that made no sense, that's okay. I'll show you. Okay? Okay, make it basic with OH, add to get water, cancel as necessary. You can also make the half reactions basic before adding them together. It doesn't really matter when you cancel as long as you remember to check your canceling at the very end to make sure you didn't miss anything. Step 7. Let's put a big red star beside step 7. Check that the reaction is actually balanced. So you're going to count your atoms, you're going to count your charge. And you're also going to check that you have no electrons. Because it's easy to make stupid mistakes. You are going to watch me forget to put charges on things all the time. What happened to my other pen? Where are you, pen? Where are you? Don't go missing on me. No, that's okay. I plugged that one back in. It'll probably be okay for a little while longer. That's irritating though. All right, shall we do this one together? Okay, so what we're going to do is, what is step 1? Isolate the half reactions. So what you're going to do is you're going to say who pairs with whom. It's almost like finding the conjugate acid-base pair, yes? Very, very similar, right? It's like, oh, I have A and I have HA, right? In this case, I have Mn and I have MnO4. That's one conjugate oxidation reduction pair. I don't know what we call it. That's not what it's called, okay? But it's like a conjugate pair. And we have our other, which is Au3 plus and Au. So we have Mn3 plus goes to MnO4 minus. Let us balance that. See how quickly you can do it. Did you guys get what I got? 4 water plus Mn3 plus, MnO4 minus, 8H plus, 4E minus. Excellent. Then what we're going to do is we're going to do our second one, which is going to be our Au3 plus goes to Au. Well, this one's easy, isn't it? No waters, no hydrogen, no nothing, just electrons. So we have isolated and balanced the half reactions. What do we do next? We make our electrons in equal our electrons going out. And we do that by finding the lowest common multiple. Who is the lowest common multiple? 12. So we're going to take this reaction here, stick it in brackets, so we're multiplying the whole thing, and we're going to multiply this whole thing by 3. We're going to take this thing, we're going to stick it in brackets, and we're going to multiply the whole thing by 4. Now, I'll be honest with you, I make so many mistakes when it comes to this. So I literally take my pen and I touch it to the page and I go, 3 times 4 is 12 waters. And then I touch the 3 again and I go 3 times 1 is 3 Mn3 plus. Yes? And then I've hit my arrow. So I'm like, okay, now I need to move to my reactants on the other one. So now I have 4 times 3 is 12 electrons plus 4 times 1 is 4 Au3 plus. So those are all the reactants, yes? That was everything over on this side here. Okay, so all of this is all of that. Yes? Now I've kind of run out of room, which is irritating. I could write smaller. Oh, I haven't run out of room. I've just made my page really big. Okay. So now we're going to go to our products, and I have 3 times 1 is 3 MnO4 minus. 3 times 8 is 24H plus. 3 times 4 is 12 electrons. And that gets me through the top half reaction and my bottom half reaction. I've got 4 times 1 is 4 gold. Now, at this point, if there is anything we can cancel, we should cancel it. Now, it's up to you. You could actually cancel your electrons up here and just be like, okay, I'm done and I don't need them. Or you can have them down here and you can cancel them down here. It doesn't matter where you cancel them as long as they get canceled. Yes? You will also check to see if there's any hydrogens or waters that need canceling. You don't have any here. And then we're good. Now, it doesn't say in basic, so we have isolated the half reactions. That step right there, that's the one that people miss that gives them electrons in their overall reaction. People will miss step number 1. They won't separate the half reactions. They'll go straight in here and they'll be like, oh, okay, I need to have 4 waters here. And that means I need 8 hydrogens over here. And that means I got a 6 plus over here. And over here I got a 7 plus over here. And that means I need a plus an electron. And I'm done. Woo! Finished balancing that redox reaction. That is completely not correct. Yes, it is not the right answer. And how do you know it's not the right answer? Because you got electrons in there. And anytime you do it that way, you will end up with electrons in there and it's just wrong. Okay, so don't forget to isolate the half reactions. You need 2 half reactions. Then you need to add them back together. So check that the reaction is actually balanced and check that you have no electrons. If you did get this, you'd be like, oh, crap, I got electrons. I did something wrong. Okay, so you'd be like, no, I cannot do that. I have to go back to square one. Down here, you don't have electrons. That's fantastic. I would actually go through and say I have 12 times 2 is 24 hydrogen, 24 hydrogen. I have 3Mn, I have 3Mn. I have 12 oxygen. I've got 3 times 4 is 12 oxygen. I've got 4 gold. I've got 4 gold. And then I would check my charge. I've got 3 times 3 is 9 positive, and 12 positive gives me a total of 21 positive. And then on the right-hand side, I have 24 positive and I have 3 negative, which gives me 21 positive. Is it a pain in the ass to check? Yes. Is it worth it? Usually yes. If you don't have time to check everything, check the charge. Because if you got those correct, chances are your atoms are probably also correct. Okay? If you have time, check everything. If you don't have time, just check the charge. Okay? All righty. How about you guys balance this one in acidic conditions? And then we'll put it into basic together. And I'll be doing it slowly up here. So if you're like, I don't know where to start, it's okay. I can walk you through it. Do you guys see what I did in my second one that's wrong already? I almost forgot the negative. I was like, oh my gosh, that would be so typical of me. So typical. Don't forget your negatives. Check your charges. Feel free to check your half reactions before adding them up. And you can tell me if I did it wrong, because it's possible I did. And you're going to tell me if I did it wrong. You got something different for which one? The first one or the second one? The chromium or the xenon? Okay.
Common is 18. Why you have 6? It's like, why you have 6? Oh. Where's my Wait, 6 electrons?
Yes, that's correct.
No, you're ending the 2. That's all right. And then you multiply this by 3.
I'm going to cancel out my electrons before I rewrite. This time I'm just going to say, okay, they're gone. Then you can put it on the next line. So what I would do is I would be like, okay, my products go on the next line. Do you know what I mean? Right? Because I often run out of room and I have to put the products down below. It's irritating, but there we are. What can we do? Oh, look, I got rid of the negative sign again. Good God. Did we get 14 H pluses on the left? Yeah. So what's going to happen is those 14 H pluses on the left are going to cancel with the 12 H pluses on the right. Yeah. So this one becomes a 2. Did we get 6 water on the left and 7 water on the right? 6, 7. Whoa. So here we go. This goes away. Okay. And we get just a 1.
That's it.
Yes. So we are now balanced in acid. Now, what if we wanted to make it balanced in base?
Oh my God, babe.
We need to add what? Hydroxide. How many? 2 to which side? Both sides. Okay.
You're joking.
And remember, when you add the OH to the hydrogen on the side with the hydrogen, that becomes water. Whew.
Oh.
Did I make a mistake?
Would you cancel the water?
Yes, I would cancel out the water. Yes. Okay, so when you get to the end, you still need to check, is there anything that needs canceling? And you say, yes, I have a water here, and I have 2 waters here, so that cancels one of them, and I'm left with 1 water on the left. Nope. Because the charge is already balanced, yes? And you're adding the same number of negatives to each side, right? Same number of oxygen, same number of hydrogen, same number of negatives on each side. Okay, so how are we feeling? Are we feeling like it's a bit of a pain in the ass, but it's manageable? Yeah? Okay. It's a pain in the ass, I'll agree. Like it's a lot of grinding and checking and grinding and yeah. Okay, but if you follow the steps, and remember at the end, we're going to check, do I have any electrons on both sides? On either side? No, that's good because this is a full reaction. Check to see, were you asked to balance a half reaction? If it was a half reaction, you should have electrons. Were you asked to balance a redox reaction? If it's a redox reaction or a full reaction, then you don't want any electrons. So we've checked electrons. What's the next thing we should check? Charge. So we're going to say over on my left-hand side, I've got 2 negative and 3 negative. So that's 5 negative over here. On this side, I've got 2 times 3 is 6 positive. I've got 3 times negative 3 is 9 negative, and I've got 2 negative. And so we get -5. Hooray! So probably, if that is the case, I don't need to check like all the hydrogens and all the chromiums and all the things. But if my charges don't match, go back and say, do I actually have the same number of chromiums? Perhaps you forgot to do the coefficient there. You know what I mean? Right? And you'll be like, oh, crumb, now I need to go back and do that half reaction again. Okay? Or you can be like, Miss Spence, can I have an extra piece of paper? Because I need to start over. And that's okay. All right? Now, no, this is easy. This is easy. There's this thing, it's called disproportionation. Everyone say it with me, disproportionation. Disproportionation. Okay. And all that means is that you have one species and some of those molecules undergo oxidation and others of those same molecules undergo reduction. So in this particular case here, if we look at this, we say, huh? How am I going to isolate my half reactions? I've only got one reactant. But you can treat it like this. Yeah? Okay. I don't even do that. I just say, okay, I got some BRs going here and other BRs going here. But if you prefer, if you're like, I don't like that, that makes me uncomfortable, you can be like, you know what? I don't know how many bromines I'm going to have, but I know that some of my bromines are going to turn into HBrO3 and some of my bromines are going to turn into HBr. Yeah? And then from there, just like the last one we did, shall we do it? This one's not as nasty as the last one. There's what? It's not that it's missing a BR. Like I said, I wouldn't bother to write this one. It just becomes confusing for people because they're like, I don't know where my other reactant is. It's just that some of these BRs turn into one thing, some of them turn into the other thing. Some of them are being, oh, look, what's this one? Is this one oxidation or reduction? Reduction. We stuck some hydrogens on it, yes? The other one is oxidation. Even though we stuck a hydrogen on it, we stuck a lot more oxygens on it, so that's oxidation. Okay? So let's try it. Am I giving myself enough room here? I think I am. Okay, we're good. Now, in this case, I've got some hydrogens on the left and I have some hydrogens on the right, so I'm going to keep track of them the same way I do the charge. So I'm going to say over here I have 12 hydrogen, and over on this side I have 2 hydrogen. That way I can, like I said, my poor little brain doesn't have to remember that. It can look at it and go, oh, that means I need 10 hydrogens over here.
No, there's 200. Yeah.
Do you want me to do it like slower?
No.
You're good?
We found the hydrogen.
Okay, 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 okay. What happened, Amy? Okay.
Okay. Now that we got through this one. Wait, and then Miss Spence.
Doesn't matter.
After that, do you do what you did for the last one?
Yeah, after this, we make our electrons in equal our electrons out. And it doesn't matter whether you write the times 5 at the beginning or the end. I got more room over here this time, so I'm going to write it there. This one we're doing an acid because it's HBr. So yeah, has to be an acid pretty much.
Yes. Yes. And then you can combine. Yeah, do that. Or no, you're adding. Oh, it's what? Oh yeah, they are on the same side. Let's see. Your oh, this. So we put all in there. Wait, and then.
Did you get a 6, 6, 10 too?
Yes.
And then what can we do with that?
Yes.
We can cancel we can simplify it by dividing everything by 2. And we're done. Yes?
Yes.
Okay. Yeah, but only certain types of equations. It'll only work for redox reactions. Okay, so now, just so you guys are aware, single replacement reactions are always redox. Synthesis and decomposition are always redox. Here, I'll write it down for you. Single replacement. Synthesis. Decomposition. And combustion. Combustion. These ones are all redox. And you can tell in a lot of them because in combustion, oxygen goes from being an element to being combined with another element in a compound. Anytime you go from 0 to 60, it's going to be redox. Now, does that mean there's not all kinds of other weird redox reactions? I mean, what the heck is this thing? That's not a synthesis. That's not a decomposition. That's not a combustion. That's just a redox reaction. Okay, but if you are looking at, you know, the very familiar reactions from last year, those are the ones that are redox, double replacement, and neutralization are not. Does anybody change their charge in a double replacement reaction? No. So all the charges just stay the same in a double replacement neutralization reaction. I don't know that this is actually like that important of a thing to know, but it's just kind of like, if you get one of those multiple choice questions where they're like, which of the following is a redox reaction, right? You can immediately eliminate double replacement and neutralization. Okay. Normally you'd just be looking for things changing oxidation number. Okay. All right. Oh, we got one more. And we got 10 minutes to do it. So that's just perfect. More than one product in a half reaction. Why is there no question? Well, that's a very good question. Let's go find the question. I must have edited it out when I took out the answer, right? So that you could fill it in. But then I must have taken out the question by mistake. So let us go, and this is what, 6.1G? Okay, let's go find 6.1G. We'll write it down. Java, Chem 12, Electrochem, 6.1G. There we go. Am I going to regret choosing the Word file? I regret choosing the Word file. Oh, no, I don't. Okay, it's good. There we go. Hang on a second. Control print screen. What? Copy to clipboard. Sure, whatever. No. That's okay. That's okay. I'll make it work. Damn it. Okay. Okay. Now I just have to make this work within the confines of this stupid thing. There we go. Okay. So you guys get to copy this down now. Mn3 plus FeSO4 gives MnO4 minus plus Fe plus SO2. And we're going to make it in basic because why not?
Here we go again.
Okay, so now, hold on. The trick, no, there are not 3 half reactions. There's only 2 half reactions. The trick is to say Mn is becoming MnO4, yes? FeSO4 is turning into both Fe and SO2. So what you're going to do is you're going to have your first half reaction, Mn3 plus goes to MnO4 minus. I think we've balanced this particular half reaction 3 times today. I feel like that one's happened a lot. And then we have FeSO4 goes to both Fe plus SO2, and that is okay. So the trick with those is to just be okay with like, oh, that has two products. But there's only one thing that can turn into both of those, right? So now we balance them. Off we go.
Wait, it is mine. Yeah. I just thought it's a binder. No, I don't know. So it should be 4 minus, right? 4E minus. And I'm trying to come this way. If we wait, I'm in there.
Well, the S is balanced, is it not? So yeah, if you had like two S's on one side and something on the other side, then you would use coefficients to balance it. Yeah? Yeah, but we don't need to do anything with it because it is balanced.
Why is there 4 also? 4.
Are we good?
So 4. Oh. And there's wait. And there's 0. So there's 4 plus. Okay. And plus 4. What? My God. Okay, so
Now, before I add these, I'm going to do my cancellation because I don't need to even do any multiplication here, right? So I'm going to cancel my 4 electrons.
and then hydrogen can turn into 4.
And I can get rid of these 4 hydrogens and just have these be 4. You could do the cancellation after you've added 2. It doesn't matter. Okay? Oh, and look, I got waters too on both sides. I got 2 waters here. That turns into 2 waters there. And now I'm going to take the whole thing and I'm going to add the 2 together. 2 H2O. So this is now balanced in acid. What are we going to do now to make it basic? Add hydroxide. How many?
4.
4, because we have 4. I canceled a bunch of things before I added.
Why is it? If it's plus 3, why is it plus on this side?
Oh, because I forgot my negative.
Oh.
Oh, look at me, they're up in a negative sign again. They always, my God. Okay. See, Tony doesn't have a messy brain.
Oh my gosh, there's the really add chicken. This is fun.
Do I need to cancel anything? Oh my God. Ay, 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 ay.
Wait, what's Miss Spence's not writing thing?
I told you, I told you guys about my Algebra 11 teacher, right? It wasn't called Math 11, it was called Algebra 11. On my last test of the year, he just didn't mark anything where I dropped my negative sign wrong because he was like, I know you know what you're doing.
Oh.
Because he just felt bad for me because all year long I'd been like, getting, Algebra 11 was not a difficult course. It was pretty straightforward. So, I'd been getting close to 100% because it was straightforward math, not hard math, but never 100% because negative signs, left, right, and center, just dropping them everywhere. Anyway, yeah, so he felt bad for me. And so on the last test, he didn't take marks off for it. Anywho, yeah, so we've got this. And then, do we need to do anything else? We need to step 7. Check. Do we have any electrons in there?
No.
Thank God. All right. What do we check next?
The charge.
The charge. So we have a 3 plus and we have a 4 minus. So that gives us -1. Over on the left, we have a -1. Oh, hey, that looks really good. And then if we had time, we could go through and say I have 1 Mn, 1 Mn, 1 Fe, 1 Fe, 1 S, 1 S, 4 O's, and 4 O's is 8 O's. 4 plus 2 plus 2 is 8, blah, 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 blah. And then you can check everything. Okay, so what I'm going to do, my question is, do you want practice with balancing half reactions in isolation? Oh, it's okay. I'll just assign some stuff. Okay. So,
We'll do the.
and then your first day back, you're going to have a quiz on question section 6.1.
Yeah.
Yay! It's either that or Friday. So I think first day back will be good because we're done 6.1 now. Okay, so that would be like having a quiz on Monday on 6.1. Yes, we have stuff tomorrow. Yes. Yes, Friday. Yes. We have section 6.2, 3, 4, and 5 to go. I'll put the homework on Teams.
Wait, how long are the classes on Friday?
Classes on Friday. 40 minutes or 0 minutes.
Okay.
And then there's like the electrochem stuff in the AP Extras booklet. We got stuff to do, people. Stuff.
Is this our last unit?
This is the last unit.
Oh, wait, did you assign it?
I think I might get you to do 6.2 on your own over the holidays.
Why are you doing
What? How would you like to finish this section in 2 weeks when we get back and do a lab? Bye. We'll get through as much of it as we can. We will. Okay. I think we can. I think we can. We got this.
Are we gonna finish it like right before the semester ends, or are we gonna have like days spare?
I don't know. We'll go as fast as we can. I'd like to have a day or two at the end. It would be nice. I've never had a day or two at the end.
Wait, I'm so-
Last time I taught this course, we had snow days,
Oh yeah.
and then there were more snow days.
Oh,
And so it was like 2 days before Christmas, it was like there were no classes, and then 2 days before the end of the semester, there were no classes. So I was like, we never did an electrochem test because we weren't able to finish it, and then there was snow. And then I was like, well,
how sucks for them though, because if you're taking the exam.
yeah, exactly, right?
That's what it is on that.
Yeah, I think so.
I remember I did not have.
I
my math.
believe we did because I was looking back through my the old team, and there's like no homework for those days, right? And there's no lesson video for those days. There's like nothing. And I'm like, why did we stop on Wednesday? Like, what happened? I assume it must have been snow days. I could be wrong. Maybe I just was like, I fell apart because it was close to Christmas, and I'm like, I don't know. I just can't post anything. Which is also a possibility, but
I
yeah.
thought you would be like on a snow day. You would be like, we're gonna have a Zoom call, guys. We're gonna have a lesson like this.
Yeah, well, I figured everyone wanted a snow day, so I put some stuff up on Teams, and that was it.
Okay.
Yeah, all right.
Yeah, it was all like the day before, though.
No,
2 years ago.
oh, 2 years ago. Could have, very easily could have.
I think it was about like the physicist. I think it was like something like that.
Oh, metallic bonding, yeah, in grade 9? Yeah, that sounds right.